All right. Hello, everybody. Thank you for being flexible today. So we're going to go ahead and we're going to pick up where we left off on problem 19. So we've got a piston cylinder assembly, contains a two-phase liquid vapor mixture of water, 200 psi, quality of 80%. It's heated at constant pressure until we get a final temperature of 480 degrees Fahrenheit. We want to find the change in specific volume, and then we're also going to draw things on a PV diagram. So let's go ahead and look at what we already did. So we got our governing equation. So our delta V is equal to V2 minus V1. And then we already fixed state 2. So in order to draw things on a PV diagram and also calculate delta V, we need to calculate or figure out what the specific volume is at state 1. And so we went to our saturated tables. We knew that it was saturated because we had a quality of 80%. So we used that quality to calculate the specific volume, and we got 1.83, and it's actually 1.835. So I went through and calculated it, and there's a 5 there. So we're going to take that into consideration. I think I just wrote 1.83 in class. All right, so let's go over to state 2. So state 2, we had figured out that it was superheated at 200 psi and 480 degrees Fahrenheit, and we knew that because the temperature T2 was greater than Tsat at P2. And so we went to our superheated tables, and of course we were at 480 degrees Fahrenheit, and unfortunately on our superheated tables at 200 psi, we only had values for 450 and 500 degrees Fahrenheit. Excuse me. Excuse me. And so we needed to interpolate for that specific volume. We got 2.654 feet cubed per pound mass. And so now I think we're ready to calculate, throw things in, and get our specific volume, delta specific volume. And so I've got a one, actually not either one of those. I guess it doesn't really matter now, does it? But whatever it is, it's 2.654 minus 1.835, and that's going to be in feet cubed per pound mass. And then of course the other thing that we needed to do, we wanted to draw things on a PV diagram, super simple. We're also, by the way, I'm going to go ahead and add that we're going to do it on a TV diagram because why not? Why not? Let's go ahead and do that. So I'm going to do my PV diagram first. So there's pressure, specific volume, got this sort of looking thing, and then over here, my TV diagram, I'll put the dome. It looks a little bit different, not too bad. All right, so clearly everything's taking place at, let's go ahead and zoom in here. It's not that much, 200 psi. And it's a constant pressure process, so I'm actually gonna constant pressure dotted line just so I know where I'm going. So it starts out at state 1, it's two-phase, and so I'm going to draw a little dot, and our quality was 80%, so I know it's kind of over to the right-hand side. So that's state 1, and then I'm going to put our specific volume. I'll label that. That's 1.85. Maybe put a little feet cubed per pound mass. Ooh, and I got to make sure that everything fits here. So here's state 2 because it's outside of that dome. And I know it is because, of course, it's superheated. So I'll put a little, there's my V2. So V1 is here. I'll put feet cubed per pound mass. And then this guy, 2, whatever that one was, 2 point something, 2.654. So 2.654, and that's feet cubed per pound mass. So we are all good there. Let's go ahead and do it on the TV diagram as well. So with our TV diagram, I kind of put it, there we go. So same thing, I know it's a constant pressure process, so I'm going to draw a little line of constant pressure, but of course it's going to be shaped a little bit differently. It's going to like that in the superheated region. This is in the There we go. So the reason I'm drawing that is because that will help me draw the process path. So at state one, I know two-phase, great. So there's state one, here's V1. Don't really need to put anything else there, I guess. I don't need to put 1.835 feet cubed per pound mass because I've defined that elsewhere. And then state two is out in the superheated region. There we go. And so I'm going to draw my process path along that constant pressure process line. What I'm not going to do is draw the line like this. That's not what I'm going to do because it doesn't go along that line. It goes along this line, across and up. And so that's what I'm looking for on a test. So if it's a constant pressure process, make sure it goes along a line of constant pressure on that TV diagram. So I'll put a little, here's a V2, perfect. T1 was not given to me. So I do need to look that up. And then T2, of course, was 480 degrees Fahrenheit. So T1, well, it was saturated, right? So this is going to be T-sat at P1 because it's the only possible pressure or temperature that I could be at and be saturated. And so actually, let's go ahead and look at that. So I'm going to go to those not superheated, saturated tables at 200 PSI, and I see the only possible temperature that I could be at would be that 381.86. So I'm going to go ahead and go over here, get that. So this is 100 and get, I forget already. 381.86. There we go. So 381.86 degrees Fahrenheit. All right. So in case anybody would like to kind of see how everything fits together there, I'm actually going to zoom in right there. That might be helpful. All right. So let's go to problem 20. All right, so we have 1 kilogram of water initially is at the critical point. If the water is cooled at a constant specific volume to a pressure of 30 bar. So, okay, so let's just go through and make sure that we see where all of the information in the given is coming from. So we've got water, 1 kilogram, and it's initially P1 and T1 are at the critical point. Okay, so that's fine. So we've got a critical temperature, critical pressure. We're right there at that critical point. If the water is cooled at a constant specific volume, and so it might not really be obvious that there's a critical specific volume. There actually is, but we'll talk about that in just a second. And then the final pressure. So constant specific volume. So V2 is equal to V1 and P2 is equal to 30 bar. Determine the quality at the final state. And then we're going to look at a different process. So for this one, starts out at the same state, at state one, but this is a constant temperature process, and we're still going to end up at 30 bar. So, okay, so let's go ahead, clean all this stuff up, and let's go ahead and start working here. All right, so for both of these, I'm going to figure out a property at state two, and I'm also going to draw it on a TV diagram and see what I've got. So for state one, I need to figure out the critical temperature and pressure. So let's go look at that. So it's like, let's make this, there we go. So this information can actually be found two places. So it can be found in table A1. So you can look up your critical temperature, your critical pressure for whatever substance. In this case, we've got water. So here's our critical temperature. Here's our critical pressure. So that's a specific point for each substance. You can also find out what the critical temperature is in these saturated tables. So this is your saturated tables water. This one's organized by temperature. So this is the last point that you see. That's your critical temperature, and this is your critical pressure. So you'll notice that, of course, this guy is in terms of degrees Celsius, and this guy is in terms of Kelvin, but it's the same 374.14 degrees Celsius. And then in the table, it's in Kelvin. So same thing. Okay. Um, Great. So actually, I'm going to fill that information in on my given here. So this guy is 374.14 degrees Celsius and P1 220.9 bar. Perfect. All right. And then the specific volume. Let's go look at that real quick. So what you'll notice, this number and this number are the same because remember the first one, this number has already been been multiplied by 1,000. So they're both 0.003155. And that makes sense. So let's see why that makes sense. So if I look at it on a TV diagram, so let's come over here. So here's my TV diagram. Go. And it's that, I'm actually going to draw it in red. It's this topmost part. Actually, I'm not loving how I drew that. Let me make it obvious that there is like a pinnacle. There we go. So here's my state one. And here's my T1. Here's that 374.1.44 that I drew on my, or that I labeled in my givens before, 374 point, oh, I'm sorry, 374.14. And then this guy right here, V1, that really, yeah, that looks good. So that's 0. Is it again? 0.003155 meters cubed per kilogram. So it's since it's a very particular spot on that dome because it's the pinnacle, then I know exactly what that specific volume is. Now, normally when when you've got something that's on the dome, well, if you got something that's on the dome, you know what the quality is, so that's enough to fix the state. Here you've got something that's on the dome, but it's like at a very specific spot on that dome, right at the pinnacle, and so there's a corresponding specific volume that goes with that. So you'll get there anyway when you look on your saturated tables because, no matter which value that you get, that you pick, this one or this one, they're exactly the same. All right. So I've labeled things on state one. I'm good there. In fact, I think what I'm going to do is because I've got two cases, right? One's a constant volume, constant specific volume process, and one's a constant temperature process. So, but regardless, they're going to be the exact same. So I'm actually, can I set over that? I'm gonna. Perfect. So it's going to be the same. It's going to start off on the same spot, but the process to state two is just going to be slightly different. Okay, so for case A, we're looking at a constant specific volume process. So let's look at that. So for state two, I know that V2 is the same as V1, which I just figured out is 0.003155 meters cubed per kilogram. And then I also know what the pressure is. So P2 is equal to 30 bar. So I'm going to look in my saturated tables to figure out what phase I'm in. Right? So let's do that. So table A3, those are my saturated tables. And these are my saturated tables that are organized by pressure. That's where I need to be. And it looks like at 30 bar, if the specific volume V2 is between the V sub F and V sub G value, then I know it's saturated. And that's exactly what I have here. My V2 is between the V sub F value, which is 0.0012165 meters cubed per kilogram, and V sub G, which is 0.06668 I'm sorry, meters. Oops. I don't know why I actually wrote the number for that one. It'd be fine, but yeah. But the V sub G, 0.06668 meters cubed per kilogram. So I know that it's saturated. So I'm going to go ahead and put that. It's saturated. Perfect. All right. So I know it's saturated, so it's going to be underneath that dome. And so actually, I think I'm good here, aren't I? So, and let's see what my temperature is going to be. My temperature at state 2 is the only possible temperature that it could be at and be saturated. So T2 is Tsat at P2, which is 33.9 degrees Celsius. Yeah. So, um, yeah, so that T1 was 374 and change. This guy is 233.9 degrees Celsius, and I've labeled it elsewhere, so I'm good there. And it's just going to go straight down, isn't it? Perfect. Clearly going straight down. All right, so there's state 1, or case 1, case A, whatever we're calling it. That's a constant volume, constant specific volume process. So now we're going to look at a constant temperature process. So, okay, perfect. So case B, I know what state 1 was, or what state 1 is. And I know what the temperature is, 344, what was it again? 374.14 degrees Celsius. And then, so I know T2 is also the same thing as T1. It's 374.14 degrees Celsius. And then I'm still ending up at 30 bar. Okay, so in this case, just constant temperature process. So I need to figure out at those two intensive independent properties, I need to figure out what phase I'm in. So I'm going to go to my saturated tables. I just happen to already be in table A2, so I'm going to use the information there. And what I can see is that at 374.14, I can see that my pressure, P2, looks like it's greater, right? P2, does it go into 30 bar? I think, yeah. Our P2 is greater than our PSAT at P74.14. Okay, so, is that right? Oh my gosh. I'm like, our P2 is 30 bar. Oh my gosh, what's wrong with me? It's less than. All right, so stupid. Okay, so it's less than the PSAT at 374.14 degrees Celsius. So it's superheated. Oh my gosh, totally got it. All right, so let's go ahead and put that there. It's superheated. So when I put things on that diagram over there, I will make sure that I draw it in the superheated region. All right, perfect. All right, so let's go ahead and draw a constant temperature process from 1 to 2, where 2 is going to end up in that superheated region. So, of course, I do, nope. Oh, there we go. I do need that specific volume, and I have figured out that yes, it's superheated. So, oh, All right, so it is superheated. So if I look at table A4, and hold on just a second because I've got some settings that need to be fixed. So hold, please. Okay, better. All right, now for some reason I wasn't able to zoom in, and that was going to be super annoying to me. All right, so we are at 30 bar. We're superheated. We're in our superheated tables. And so I can see, well, let's see, what can I see? Because this might be a little bit difficult. So I do have my T2. It's a little bit smaller. So T2 was 374.14. So unfortunately, I'm right there. 374.14. So 374.14, which means that I am going to have to interpolate between these two guys to get that specific volume. So I do need to interpolate. So my V2, which is the specific volume at T2, 374.14 degrees Celsius, and P2, which is 30 bar, ends up being, so it should be between 0.0923 and 0.09994, and I end up getting 0.0948, and it's meters cubed per kilogram. Perfect. So just make sure that you could interpolate and you get that same thing. But yeah, so 0.0948 meters cubed per kilogram. There we go. So here's state two, case B. And I believe we've got two more, so let's go ahead and plow through those guys as well. All right, so problem 21, we have a closed rigid tank. And remember what assumptions that we make about a closed rigid tank. We say that this, make that black and make that a little bit thicker. We say that our change in volume is constant, and since our mass is constant as well, our change in specific volume is 0. So that's going to help me fix state 2, right? Because I need two independent intensive properties with which to fix my state, and so I'm going to need that at state 2. Perfect. So I need to figure out the initial and final pressures. I also need to locate the initial and final states on a PV and TV diagram. So yeah, if I just draw a PV and TV diagram, I'm going to have accomplished those things. All right. So at state 1, of course, I'm going to go to my saturated tables. And because I know that T1 is 200 degrees Celsius, and they told me point blank it is a saturated vapor, I also know that the quality is 1, right? And that is because, again, they told me point blank, you have a saturated vapor at state 1. And so I'm going to go to my saturated tables and, oops, I'm going to be, yeah, there we go. Go to my saturated tables, and it looks like at 200 degrees Celsius, I know what my P1 is because I know it's a saturated vapor. It's saturated, so only pressure that it could be at is my saturation pressure, and that's 15.54 bar. Also going to need that V1, and it's V sub G at T1, right? Because my quality is 1. You could also, again, you could plug it in. Write this first. You could plug it in to that V sub F plus your quality times V sub G minus V sub F. But of course, since your quality is 1, you're going to find out that it's V sub G anyway. So, just be aware of that. Okay, so I've got all the stuff that I need for state 1. So actually, I think, yeah, I'll wait on drawing things on the PV and TV diagram. Let's go ahead and let's look at state 2. So at state 2, we've got 240 degrees Celsius, and then the specific volume is the same at state 1 and state 2. So let's see. So my P2, oops, not my P2. I don't know that yet, do I? So let me erase that. Um, my V2, I do know that because it's the same as V1. It's a rigid tank. Volume's the same, specific volume is the same. So 0.1274, 1274 meters cubed per kilogram. And then the other thing that they told us is they told us what the temperature is. So our T2 is 240 degrees Celsius. And so I'm going to go to my saturated tables, not because I'm assuming that it's saturated, but because I need those things to fix my state. So I'm going to go to table A2, my saturated tables that are organized by temperature. I'm going to go to this little line, go to this little line corresponding to 240. And what I'm going to find is that my specific volume, V2, 0.1274, it's above this V sub G value. So it's above my V sub G at T2. And so that tells me that it's superheated. All right. So let's go to our superheated tables. So these are our superheated tables for water. All right, so table A4. So for table A4, now normally when I go to those superheated tables, I'm really lucky because I know the pressure, and so I go to the box corresponding to that pressure, but I actually do not have the pressure. All I have is the temperature and the specific volume, but that's still enough to fix my state. So I'm going to tell you what I'm going to be doing. I am going to be looking, I'm going to go to my saturated tables, and I'm going to be looking along those lines corresponding to 240 degrees Celsius. And remember my specific volume. I'm actually going to put it over here. So remember that's 0.1274 cube per kilogram. So what I'm going to be doing is I'm going to be looking at these values, specific volume, and I'm going to try to find some specific volume values that are around 0.1274. So it looks like in between, it's like I've got a value right above 0.1274 and right below 0.1274. And so what I'm going to do is I'm going to organize that information into kind of my own table. Okay? So I've done that down here. So my value, I am looking for, I'm looking for a P2 value at 240 degrees Celsius and 0.1274. Well, I have a value at, let's see, 0.1483 and 240 degrees Celsius. And that pressure is 15 bar, so 0.1483. 0.1483. This pressure is 15 bar. And I'm going to tell you, it won't matter, but just so it looks a little bit better and nobody's thinking it shouldn't be what it is, I'm going to put that on the second line. The reason is because now I'm going to look at this guy right here. So I have a value for 200 a value of pressure for water at 240 degrees Celsius and 0.1085 meters cubed per kilogram. All right, and the pressure for that one is 20 bar. So it's really obvious that my pressure should be between 15 and 20 bar. So what I'm trying to show you here is that you can organize when you're interpolating, you can kind of create your own little table and organize it so it looks consistent, right, in the same manner that are, I guess, in the same form that we're used to interpolating with. Because it's not always going to be organized on the actual table that you can look up on that PDF. It's not always going to be organized like that. All right, so you might have to make your own little table here. All right, so if I interpolate now, I'm going to get a value of, I'm going to get, 17.63. So this ends up being 17.63 bar. All right, so now I have a pressure at state 2. So let's go to draw things on my PV, my TV diagram. So on my TV diagram, so at state 1, I know it was a saturated vapor. At state 2, I know it was superheated. So I just need to make sure that I draw things draw things in the right places corresponding to that vapor dome. So here's state 1. State 1 was 200. And my specific volume, same at state 1 as it is at state 2. And that should be a 2, sorry, 0.1274. And that's meters cubed per kilogram. And then state 2, I figured out what well, no, I was given what my temperature is. My temperature is 240 degrees Celsius. And I know, go right up, and it's going into that. It's clearly in that, well, maybe not. There we go. Yeah, so I can, there's clearly a space between state 2 and the vapor dome. So, on a test, you might have to sort of like make that vapor dome like a little bit smaller to make it absolutely obvious that, or a little bit thinner, I guess, to make it obvious that you're not saying it's a saturated vapor, you're saying it's superheated or showing it as superheated. And then over here for our temperature, so, or our PV diagram, it's going to be the same thing. So it's also going to go up like this. So this is state 1, this is state 2, this is V1 is equal to V2. Sorry about that little comma there. I'm going to delete that. There we go. And we had figured out what P1 was. So P1 was the saturation pressure at 200 degrees Celsius. We found that to be 15.54 bar. And then we just interpolated and saw P2 is 17.63 bar. Perfect. So I've drawn everything, I've labeled 1 and 2. I've drawn it, states 1 and 2 in relationship to the dome, the vapor dome. I've labeled the temperatures and pressures and specific volumes. And so that would be full credit for me. And I've also made a note of, the units there as well for all of those things. Okay, so let's go to the last problem. And that will be it for Unit 1, and then you'll be ready to take your test if you so wish. Just remember that test is actually open for a while. It'll be open until Wednesday night. So that's the 7th. So if you have questions, when we get back on Wednesday, you just let me know. Come right before class, come during office hours, whatever. All right, so problem 2, we have a water with a quality of 90% in a piston cylinder. It's heated at a constant pressure from 210. So that was our T1 from 210 degrees Fahrenheit to a final temperature of 300. And we want to draw the process on a TV diagram. So easy peasy. Let's go ahead and get our specific volumes because that's kind of all we need to draw things on that TV diagram. So let's do that. All right. So state 1, I know the quality, and T1, 210 degrees Fahrenheit. And so at state 1, it is clearly going to be saturated because I have a quality. Quality has no meaning if it's not saturated. And so I'm going to go to my saturated tables organized by temperature, and I have a column for 210, so that's great. So my specific volume it's going to be V sub F plus my quality times V sub G minus V sub F. And so I end up getting 0.0167 times, plus 0.9 times 27.82 minus 0.0167. And then all of these, let me make it obvious that units apply out here. These are going to be feet cubed per pound mass. And so I get a V1 value. Let's see what I end up getting. I've got 25.04. And that's going to be in feet per pound mass. All right, so state one, got that taken care of. Now we're going to go to state two. So state two, we have, it's a constant pressure process. So P2 is equal to P1, and then I know V2 is, know anything about V2, but I do know what T2 is. It's going to be 300 degrees Fahrenheit. Now, unfortunately, they didn't actually tell me. They just said it was a constant pressure process, but they didn't tell me what that pressure was. But that's okay because I had enough information to fix state one because I knew what the temperature was and the quality was. And so I know that the only possible pressure that it could be at state one is the saturation pressure at T1. All right, so in A2E, in my saturated tables that are organized by temperature, I see that the saturation pressure is 14.13 psi, right, pound force per square inch. So I'm all good there. Now I need to bring that information over to state two to help me fix my state. All right, so let's come over here. So this is, we figured this was 14.13 degrees, or not degrees, psi. All right. So first thing I need to do, go to my saturated tables, figure out what phase I'm in. So I'm here in table A2E, and I can see that, so these are the tables that are organized by temperature. So 300, there we go, 300 degrees Fahrenheit. I could see my pressure, my saturation pressure is 66.98, and my pressure, P2, is less than Psat at T2, which means that I'm superheated and I need to get out of those saturated tables and go to my superheated tables, So that's exactly where I'm going to go. All right. So again, E2, let me put it in here, 14.13 psi, T2, 300 degrees Fahrenheit. And unfortunately, dang it, normally I have a pressure, and normally I go to the box corresponding to that pressure, but I don't have that. So what I'm going to have to do, I'm going to have to do another one of those one of those interpolations. So I've got a box for 10 psi and a box for 14.7 psi. And I've got specific volume values for 300 degrees Fahrenheit for both of those. So what I'm going to do, I want you to take a note of this number, this number, this number, and this number, because I'm going to bring it down in the table that's below, and I'm going to create my own little table that I can interpolate really easily in. All right, so at 300 psi, we had values for 10 psi, 14.7 psi, but I want, I don't know why I've got 4 spots there, 14.7 psi, and I want my value at 14.1 for 14.13 psi. So at 300 degrees Fahrenheit and 10 psi, the specific volume is 44.99 at 14.7 and 300 psi or 300 degrees Fahrenheit. It is 30.52. And so this is my V2. And if I interpolate, it should be between the 30.52 and the 44.99. And it is. I end up getting 32.27 feet cubed per pound mass. All right, so I think I've completely fixed my state. Right, perfect. So I think now I am ready to draw things on that PV and TV diagram. So let's go ahead and go do that now. All right, so I've got a TV diagram all ready to go. I don't know why I don't have a PV diagram, but there you go. All right, so state one, it was saturated vapor. State two, it was superheated. So I do need to, you know, sure I'm kind of ready to draw my states there. So state one is going to be on that saturated vapor line. So here's state one. And I know that it was a constant pressure process. So I'm just going to go ahead and kind of at least draw like a little dotted line here so that I can see that from state one to state two into that superheated region, it's going to go along a line of constant pressure. So there's state two. Here's my T1. T1 was given to me, I believe. Yep, this is, and it's written elsewhere, but it's 210 degrees Fahrenheit. T2 is, what was that? 300 degrees Fahrenheit. V1, V2, those are written elsewhere. My units are included, but yeah, I'll go ahead and put this is 32.27 feet cubed per pound mass. And this guy was, we calculated 25.04 feet cubed per pound mass. There we go. So there's my TV diagram. Let's go ahead and do the PV diagram, and that will be it. There we go. PV. All right. So there we go. There's my, I don't like that. That looks awful. It doesn't look much different, but it's okay. We'll stick with it. All right. So state one, I know that it's a saturated vapor. So it's going to be right there on that saturated vapor line. And then it's going to go along a line of constant pressure all the way out here. So go straight across. Here's my V1. Here's my V2. Of course, that's listed elsewhere. This pressure right here, we've already calculated, was our saturation pressure at 210 degrees Fahrenheit. So it's 14.13 psi. That's our pressure. And so I've clearly labeled that. That's P2, same as P1. There you go. I didn't put a number on that diagram for V1 and V2 because I've already put it other places. And so it's enough. It tells the story, gives me all the information there. And I don't have to look too hard for it. All right. Um, so Labor Day is on Monday, so the university is closed. So we do not have class on Monday, and we won't meet. And then we'll start Unit 2 on Wednesday. I currently have your test. It's open. It's ready to go. It's open until Wednesday night at 11:59. So if you do have questions, I'll have office hours Wednesday morning. As normal, I'll come in about 30 minutes earlier. I also have them, 12:50 to 1:20 if you want to come at that time as well in my office. So, and then the TA also has office hours on Tuesdays and Thursdays. I think perfect. I think I need to update that. Yeah, so he has office hours Tuesday and Thursday 3 to 4, and then she has office hours Friday until 11:30, 10:30 to 11:30. But that's there's an announcement, and I'll update that on the Canvas website so that you have that in two places. Okay. So if you have questions, please feel free to reach out. Other than that, have a wonderful weekend. I will see you in class on Wednesday. Okay? All right. Thank you.